Nothing in the universe can be older than the universe itself. That much is simple logic, not a discovery. And no serious scientist studying this topic has ever claimed otherwise, whatever eye-catching headline framing might suggest to a casual reader scrolling past. But in 2023, and again in 2024, the James Webb Space Telescope found something that came close enough to breaking that rule to genuinely alarm professional cosmologists. Galaxies so massive, so structured, and so mature that they appeared to have needed more time to form than had actually passed since the Big Bang. Not objects older than the universe itself, which is impossible under any physical framework taken seriously today, but objects that looked like they belonged to a much later, much older chapter of cosmic history than the timestamp stamped on the light reaching our telescopes. Astronomers have taken to calling them, informally, universe breakers, and years later, the scientific community still has not fully settled what to make of them, even as follow-up observations continue rolling in from Webb's ongoing survey programs. To understand why this discovery rattled people who study the early universe for a living, it helps to walk through what astronomers expected to find before Webb ever launched. The Big Bang occurred roughly 13.8 billion years ago, and for a long stretch of time immediately afterward, the universe was too hot, too dense, and too chaotic for anything resembling a star or a galaxy to exist, filled instead with an opaque, glowing plasma of subatomic particles that light itself could not travel through freely. Only gradually, as the universe expanded and cooled over hundreds of thousands of years, did neutral atoms finally form, allowing light to travel freely for the first time, and setting the stage for gravity to slowly begin pulling together the first clumps of gas dense enough to eventually ignite into stars. Only after that did those early stars and their surrounding gas begin merging into the first small, primitive galaxies, a process astronomers refer to as the era of cosmic dawn. Existing models of galaxy formation, built and refined over decades using both theoretical physics and prior observations from telescopes like Hubble, predicted that this process should be slow and gradual, unfolding in careful stages across hundreds of millions of years. The very first galaxies, forming a few hundred million years after the Big Bang, were expected to be modest, dim, disorganized collections of stars, something closer to a loose cosmic sketch than a fully realized galaxy, still actively assembling themselves out of scattered pockets of gas and young stars, building something the size and mass of our own Milky Way, containing roughly 100 billion stars arranged into an organized, rotating structure with defined spiral arms and a central bulge, was expected to take billions of years of steady accumulation, collision, and gradual growth through repeated galactic mergers. A galaxy that size showing up too early in cosmic history was not supposed to be possible under any version of this framework, because there simply would not have been enough time for gravity to pull that much material together and organize it that thoroughly, regardless of how favorable the local conditions happened to be. Webb was specifically built to test predictions like this directly. Unlike Hubble, which primarily observes visible light, Webb is tuned to detect infrared light, and that distinction turns out to matter enormously for studying the distant past. Light from extremely far-away objects has been stretched by the ongoing expansion of the universe itself during its long journey toward us, a phenomenon called redshift, which pushes visible light from the earliest galaxies out into infrared wavelengths by the time it finally reaches our instruments. The same basic principle behind why a passing ambulance siren sounds lower-pitched as it moves away from you. Hubble could catch only glimpses of the most distant galaxies, and even then only the brightest, most extreme examples, since its instruments were simply not tuned to pick up the heavily redshifted infrared light coming from the very earliest cosmic epochs with much sensitivity at all. Webb, built specifically to observe deep into the infrared with much greater sensitivity and a much larger primary mirror than Hubble's, was designed to look further back into cosmic history than any previous instrument, essentially functioning as a time machine capable of directly imaging light that has been traveling toward Earth for well over 13 billion years, arriving now as a faint, stretched-out infrared glow rather than the visible light it started out as. In February of 2023, an international team of astrophysicists from the United States, Australia, Denmark, and Spain, including Erica Nelson at the University of Colorado Boulder and Ivo Labbé at Swinburne University of Technology in Australia, published findings describing 6 candidate galaxies buried inside Webb imaging data gathered through a survey program called SEERS, the Cosmic Evolution Early Release Science Survey. The images covered a patch of sky near the Big Dipper, a region Hubble had already photographed decades earlier without noticing anything particularly unusual there, dismissed at the time as a relatively unremarkable, quiet stretch of sky. Nelson has described how she first noticed the objects almost by accident, spotting a handful of oddly bright, unusually red dots while examining a small, postage stamp-sized section of the imaging data for an entirely different research purpose. Dots that looked, in her own words, too bright and too red to be real. Follow-up analysis suggested these 6 candidate galaxies existed remarkably early in cosmic history, somewhere between roughly 500 and 700 million years after the Big Bang, meaning the light captured by Webb had been traveling toward Earth for more than 13 billion years before finally reaching the telescope's mirrors. What made these particular objects so startling was not simply their age, it was their apparent size. Despite forming at such an early point in cosmic history, these candidate galaxies appeared to contain nearly as many stars as the modern Milky Way does today, a galaxy that took the vast majority of the universe's entire history, some 13 billion years, to build up to its current size and structure. Nelson's blunt reaction, quoted at the time, was that the finding was simply bananas. And she went on to explain that nobody studying galaxy formation expected the early universe to be capable of organizing itself into structures this large, this quickly. According to existing theory, these galaxies should not have had anywhere near enough time to form, let alone reach a size rivaling one of the largest, most fully developed galaxies known to exist in the present-day universe. A separate, arguably even more striking discovery followed roughly a year later. In early 2024, a research team studying a galaxy formerly cataloged as ZFUDS 7329 announced that this particular object, formed only around 800 million years after the Big Bang, contained more stars than our own Milky Way currently does, despite existing at a point in cosmic history representing less than 6% of the universe's total current age. Unlike the 6 candidate galaxies from the 2023 SEERS study, which relied primarily on photometric estimates, ZFUDS 7329 was studied through detailed spectroscopy, a slower but far more reliable technique that splits an object's light into its full range of individual wavelengths, rather than relying on a handful of broad color filters, giving researchers considerably more confidence in the resulting age and mass estimates. The scientists behind that study described the finding as posing a significant challenge to the standard model of cosmology, the widely accepted framework describing how matter, dark matter, and cosmic expansion have shaped the universe's structure over time. Under that standard model, galaxies are expected to form gradually around dense concentrations of dark matter, which act as a kind of gravitational scaffolding that ordinary visible matter later collects around and condenses into stars. A galaxy this massive appearing this early suggests either that it formed without the usual dark matter scaffolding guiding its growth, directly contradicting how galaxy formation is generally understood to work at a fairly fundamental level, or that something about conditions in the early universe allowed matter to organize itself dramatically faster and more efficiently than existing models account for. Neither explanation sits comfortably within current cosmological theory, and researchers studying the object have been candid that they do not yet have a fully satisfying answer for how it came to exist in the form and size that Webb observed, leaving the case open as one of the more genuinely puzzling individual objects currently on record. Alongside these unusually massive early galaxies, Webb's deep imaging surveys have also turned up a separate related mystery, an abundance of strange, extremely compact, intensely red objects that astronomers have nicknamed somewhat informally little red dots. These objects showed up in far greater numbers than anyone expected once Webb began systematically imaging deep fields of the early universe, appearing repeatedly across multiple independent survey programs, rather than as an isolated fluke confined to one particular patch of sky. And their true nature remains genuinely unresolved years after they were first noticed in the data. Some researchers believe at least a portion of them may be compact, actively forming galaxies, dense knots of star formation glowing intensely enough to appear deceptively small and concentrated from our vantage point, essentially entire young galaxies compressed into a footprint far smaller than astronomers would normally expect. Others suspect many of these red dots may instead be active galactic nuclei, meaning supermassive black holes actively feeding on surrounding gas and dust at the centers of otherwise faint, hard-to-detect early galaxies. Their intense glow drowning out the fainter light of the host galaxy surrounding them and making the whole system appear as a single, compact point of light rather than a diffuse, extended structure. Determining which explanation applies to which object matters enormously for the broader mystery, since if a meaningful fraction of these little red dots turn out to be genuine, fully formed galaxies rather than black hole activity, that would add substantially to the growing list of objects that appear too massive, too structured, or too mature for how early they existed in cosmic history, compounding the puzzle already posed by the SEERS candidates and ZFUDS 7329, and pushing the overall statistical case for a genuine cosmological tension even further beyond what a handful of isolated, unusual objects could plausibly represent. Cornell astrophysicist Joel Leja, who has worked extensively on interpreting this data, put the underlying challenge plainly. noting that before astronomers rewrite established cosmological theory to explain how these objects assembled so quickly, they first need to rule out the possibility that what appears to be an impossibly massive early galaxy is actually something else entirely, a distinction that itself typically requires entirely new theoretical concepts to properly explain either way, since even the alternative explanations on offer tend to stretch existing physics in their own right. It's worth being clear about exactly how tentative some of this remains, because responsible science reporting on this topic has to hold two things true simultaneously: that the tension is genuinely real and taken seriously by working cosmologists, and that not every eye-catching early claim has survived closer scrutiny unchanged. Webb's initial detections of these objects rely heavily on a technique called photometric analysis, essentially estimating an object's distance, age, and mass based on the specific colors and brightness levels captured across a handful of filtered images. A method that is fast and effective for surveying enormous numbers of candidate objects across a wide field of view, but considerably less precise than direct spectroscopy. A slower, more resource-intensive technique that splits an object's light into a full, detailed spectrum to pin down its properties with far greater confidence at the cost of requiring dramatically more telescope time per object studied. As follow-up spectroscopic observations have gradually been carried out on some of these candidate massive early galaxies, a portion of them have had their estimated masses and distances revised. In some cases, downward, once more rigorous data became available, a normal and expected part of how frontier astronomical claims get tested and refined over time, rather than evidence that the entire phenomenon was mistaken from the start, much the way early estimates in any fast-moving scientific field routinely get sharpened as better instruments and more careful analysis become available. Even accounting for that necessary caution, however, a meaningful number of these unusually massive early galaxies, including cases studied through detailed spectroscopy rather than photometry alone, such as ZF-UDS 7329, have held up under closer examination, keeping the core tension with standard cosmological models genuinely unresolved rather than dismissed as an artifact of imprecise early measurement. The scientific stakes riding on properly resolving this mystery are considerably higher than they might first appear. The standard model of cosmology currently used to describe the universe's overall structure and history, generally referred to by the shorthand ΛCDM, has proven remarkably successful at explaining an enormous range of observations gathered over decades. From the detailed pattern of the cosmic microwave background, radiation left over from the Big Bang itself, to the large-scale distribution of galaxies observed throughout the nearby universe, to the measured rate at which the universe continues expanding today. If a meaningful population of galaxies genuinely did form far faster and far larger than that model allows, it would represent a serious gap in one of the most thoroughly tested scientific frameworks currently available, potentially requiring adjustments to how scientists understand the role dark matter plays in seeding galaxy formation, or how efficiently early stars were able to form and merge together during the universe's first several hundred million years, a period astronomers sometimes refer to as the cosmic dark ages and cosmic dawn, still poorly understood compared to almost any other chapter of cosmic history simply because no instrument before Webb had the sensitivity needed to observe it directly. Some researchers have proposed that early star formation may simply have proceeded far more efficiently than current models assume, converting available gas into stars at a faster rate than expected, potentially without needing to abandon the broader dark matter framework at all, a comparatively modest fix that would preserve most of the existing theoretical structure, while still requiring meaningful revision to specific assumptions about star formation efficiency. Other researchers have raised the possibility that gravitational lensing, a phenomenon in which the gravity of a foreground galaxy or cluster bends and magnifies light from a much more distant background object, might be inflating the apparent brightness and inferred mass of some of these candidate galaxies, making them look larger and more massive than they actually are once that magnifying effect is properly accounted for and subtracted out of the measurements, untangling exactly how much of this puzzle reflects a genuine crack in cosmological theory, and how much reflects the ordinary growing pains of using a brand new instrument to study a region of cosmic history nobody has ever directly observed before remains an active, unresolved area of research, with new papers on the topic continuing to appear at a steady pace. There's also a broader historical pattern worth keeping in mind here, one that tends to get lost in headlines proclaiming the imminent collapse of established physics. Nearly every major new observational instrument in the history of astronomy has, at some point shortly after coming online, produced results that initially appeared to strain or even contradict existing theory, only for those apparent contradictions to eventually resolve themselves, sometimes through refined observations, correcting an early overestimate, and sometimes through genuine, meaningful revisions to the underlying theory itself that ended up improving scientific understanding rather than undermining it. Webb's early massive galaxy problem may ultimately resolve in either direction, or more likely in some combination of both, with certain specific claims eventually being walked back through more careful follow-up observation, while other core findings hold up and force real, lasting revisions to how astronomers model the universe's first several hundred million years. What makes this particular moment genuinely different from prior instrumental growing pains is the sheer volume and consistency of the anomalous findings accumulating across multiple independent research teams, multiple survey programs, and, increasingly, multiple confirmed spectroscopic follow-up studies rather than photometric estimates. Alone, a pattern of consistency that makes simple observational error a progressively less satisfying explanation the longer it persists across independent datasets. For now, the honest scientific position sits squarely between sensational headline and complete dismissal. Webb has not photographed anything literally older than the universe, since that remains logically impossible under any physical framework currently taken seriously by working physicists. It has not captured an artificial megastructure of any kind, and no credible research team studying this data has proposed anything resembling that explanation, nor has any serious peer-reviewed analysis suggested these objects involve anything other than natural astrophysical processes. However poorly understood those processes currently are. What Webb has done is considerably more interesting than either of those exaggerated framings, quietly building a growing catalog of galaxies that appear too large, too structured, and too chemically mature for the extremely narrow window of cosmic time available to have produced them under current theoretical models, a genuine open puzzle sitting at the frontier of modern cosmology, still being actively investigated through new observations, refined statistical methods, and updated theoretical models years after the first unsettling detections were made public in early 2023. This is, in many ways, exactly the kind of moment scientists hope for when a genuinely new instrument comes online, a body of evidence strange enough to force real re-examination of assumptions that had otherwise gone largely unchallenged for decades, precisely the sort of productive friction that tends to drive meaningful scientific progress forward rather than simply confirming what everyone already expected to find. Whether the eventual resolution turns out to favor faster, more efficient early star formation, some previously unaccounted for role for supermassive black holes in shaping these compact early systems, revised statistical treatment of gravitational lensing effects, or some combination of factors nobody has fully articulated yet. The process of working through this puzzle is already reshaping how the next generation of cosmological models gets built and tested. Additional Webb observing time continues to be allocated specifically toward following up on these candidate objects, and researchers are increasingly prioritizing spectroscopic confirmation over photometric estimates, precisely because of lessons learned from this exact controversy, a methodological shift that should, over the coming years, considerably sharpen the picture currently available. Somewhere out at the edge of what Webb's mirrors can currently resolve, light that began its journey more than 13 billion years ago continues arriving at our telescopes each night, carrying with it a question nobody has fully answered yet: exactly how the universe managed, apparently, to build so much so quickly during the very first sliver of its own existence. That question will likely take years more of careful, methodical work to resolve, involving deeper spectroscopic follow-up, refined theoretical modeling, and quite possibly entirely new observational strategies not yet conceived. But it is a question grounded firmly in real, peer-reviewed data gathered by one of the most capable scientific instruments humanity has ever built, not in speculation about lost civilizations or structures beyond physical law. And that grounding is exactly what makes it worth taking seriously, rather than dismissing as either impossible or inevitable.